Solving systems of linear inequalities. Linear programming is a method of finding a maximum or a minimum value of a function that satisfies a given set of conditions, which we call constraints. A constraint is one of the inequalities in a linear programming problem, or a system of linear inequalities. That's what a linear programming problem is. The solution set of constraints is called the feasible region. And the feasible region is marked off with vertices or vertex. So let's do an example of graphing constraints of a linear inequality. But the first thing we have to do is actually create the constraints. So in this first one here, Yum's Bakery bakes two different types of bread, A and B. One batch of A uses 5 pounds of oats and 3 pounds of flour. One batch of B uses 2 pounds of oats and 3 pounds of flour. The company has 180 pounds of oats and 135 pounds of flour. We want to write a system of inequalities that represents this information. So what I'm going to start with is my batch of oats. How many oats do we have? We have 180 oats. That's the maximum. So that means that our bread has to use less than or equal to 180 pounds of oats. Now the oats for batch A is 5 pounds, so that would be 5, and let's just call X my A, plus 2 pounds of oats for the bread B, so 2Y. So 5X plus 2Y is less than or equal to 180. And then we have the flour. We have 3 pounds of flour in A, 3 pounds of flour in B. So that means 3x plus 3y must be less than or equal to 135 pounds of flour total, so 135. However, we can't stop here because we cannot have a negative amount of flour or oats. So that means we have two more constraints we have to put in. X must be greater than or equal to 0, and y must be greater than or equal to 0. And those would be my constraints to this linear programming problem. What we want to do is actually graph these constraints. Well, x is greater than 0 is easy. It's just where is my x greater than 0. Y is greater than 0 is also easy because they're just going to mean it's going to be in the first quadrant. So x is greater than 0 is right here, and y is greater than 0 is right here. All right, now we graph the rest of them. So 5x plus 2y is less than or equal to 180. And 3x plus 3y is less than or equal to 135. So this we graph the same way we graphed our other equations. So I'm just going to put them on there. And right here, there's one of our constraints. And our other constraint is a steeper line. And it's going to be about right here at 36. And there we go, something like that. So if you actually take the time to graph it nicely and everything, then that should be what you get. And then if you shade it in, it should be the intersection right in here. So double check to make sure that you got the same graph as me. But that should be your final answer. And your intersection points, let's mark those. Right here, this is actually going to be the point 3015. This is going to be the point 36, 0. This is the point 0, 0, obviously. And then we have the point up here, which is 0, 45. These points are going to be important in our next example. As I said before, we often want to find the best value of a linear programming problem, and that's what we're going to do next. We often want to find the best combination of values in order to maximize or minimize a certain function. This function is called the objective function. What are we trying to accomplish? We can prove that the maximum or the minimum value of the objective function will always occur at a vertex of the feasible region, which is why I mentioned that the vertices are going to be the important part of that last part. So we're going to use those vertices to maximize a function. Alright, so we have Yum's Bakery wants to maximize its profits from its bread sales. One batch of A yields a profit of $40, and one batch of B yields a profit of $30. Use the profit information and the data from the feasible region to find how many batches of each bread the bakery should make. So $40 for every batch of A, so 40 times however many batches of A plus 30 times however many batches of B they make, that's going to be their total profit. So your objective function is 40A plus 30B equals P dollars. So we're going to just put in our X and our Y. So technically, instead of saying A and B, we should have said X and Y, but it doesn't really matter as long as we know what things correspond to. So I need to find my profit for each of these different vertices, because these are the vertices from before: 0, 0, 0, 45, 30, 15, and 36, 0. So I'm going to put in 40 times 0 plus 30 times 0, and if I multiply that out, obviously I get $0. The next one, 40 times 0 again, plus 30 times 45, and then 40 times 0 is 0, so the 30 times the 45 is going to give us $1,350. Okay, so clearly that is the most so far. All right, the next one, 30 and 15, so 40 times 30 plus 30 times 15, and if I multiply those and then add them together, I get $1,650. Okay, so now that one's the most so far, but we got to try the last one. 40 times 36 plus 30 times 0. 40 times 36 is going to give me 1,440 plus 0, so $1,440. And then I find which one is the most. So clearly the 1,650 is the highest value, so they should make 30 batches of A and 15 batches of B. And that's what they should do. And if they do that, then they should get a profit of $1,650. That's it for your notes over solving systems of linear inequalities. Go through the practice problems because this is kind of hard to understand, because you will have to understand how to create your feasible region, create your constraints, draw your feasible region on the graph, and then how to maximize your objective function. You'll have to be able to do all of those things. So go through the practice problems and then prepare for your quiz.